All right, today we are diving deep into one of the most incredible frontiers in science, brain-computer interfaces. We're going to explore how researchers are tapping directly into the brain's own signals to give a voice back to people who've lost theirs. It's fascinating stuff.
So, let's just start with this. What if you could actually speak, just by thinking? Imagine your thoughts appearing as words on a screen, or even spoken out loud by a synthesized voice. Now, for millions of people living with conditions like ALS or the effects of a stroke, this is not science fiction. It's the ultimate goal, a quest to restore one of the most basic things that makes us human, our ability to connect with each other.
To really get why this is such a big deal, we need a baseline. You and I, when we're just talking, we speak at about 150 words per minute. It's the speed we totally take for granted, right? It lets us have these fluid, natural conversations. It's fast, it's expressive, and it's us.
Now, look at this gap. This is what's so wild. The best assistive tech we have right now, things that track your eye movements to pick letters on a screen, they max out at around 10 words per minute. And that's if everything's going perfectly. We're talking about a massive drop from 150. That huge canyon in between, that's what speech BCIs are trying to fill, to get us from slow, frustrating typing back to the actual speed of thought.
And this really brings us to the heart of it, the human reason that's driving all this mind-blowing science. This is about so much more than just cool tech. It's about connection. I mean, think about people who are locked in. They're fully conscious, but they can't move or speak. For them, getting their ability to communicate back isn't just some nice-to-have feature. It is the top priority. It's about talking to your family again, expressing what you need, and just feeling like yourself. The drive for a real solution here is just immense.
Okay, so let's get into the engineering a bit. If you want to decode thoughts, first you have to listen to them. And right away, that presents this really fundamental choice. How do you get a good, clean signal from the brain?
And this lays out the central trade-off perfectly. On one side, you've got non-invasive sensors, like an EEG cap that just reads brainwaves from your scalp. Totally safe, no surgery needed, but your skull acts like a big muffler, making the signals pretty noisy and hard to read. On the other side, you have implanted sensors. These are tiny grids placed on the surface of the brain or even little arrays that go just inside it. Now, this means surgery, which is a big deal, but the signal you get, it's incredibly clear, it's super high fidelity.
So, which do you choose? Well, when researchers ask potential users, the answer is actually pretty clear. Most people say they are willing to have the surgery. But, and this is a big but, the system has to actually work really, really well. We're talking better than 90% accuracy. If it can genuinely give them back fast, reliable communication, then yeah, for them, the benefit is absolutely worth the risk. All right, now for the breakthrough part. For decades, the dream of a BCI that could decode speech this well felt pretty far off. But just in the last few years, progress has been accelerating like crazy. So how did we finally start to crack the code?
The answer, in a word, is AI. Specifically, these deep learning algorithms that are just unbelievably good at finding patterns in messy, noisy data. Researchers are basically feeding these AIs the brain signals and teaching them to translate the complex firings of neurons into the sounds, the syllables, and finally the full words someone is trying to say.
And the results? They've been nothing short of spectacular. Check out this timeline. It shows the word error rate, basically the percentage of words the system gets wrong. Back in 2021, a big study hit a 25.6% error rate, which was amazing at the time. By 2023, it was down a little to 23.8%. But then, a study in 2024, it dropped all the way to just 2.5%. That is a massive leap in just 3 years.
I mean, to put that 2.5% error rate into perspective, that's 97.5% accuracy. That's good enough for real, everyday communication. In one of these trials, a participant with severe paralysis used the system to chat with their family, join video calls, and even write work emails. This stuff is officially leaving the lab and starting to change lives.
But, and there's always a but, this explosion of progress, especially with non-invasive BCIs, has created a totally new, kind of hidden problem. With all this success comes a new kind of chaos.
Yeah, it's one of those good problems to have, right? All of a sudden, you've got dozens of labs all creating their own amazing AI models for decoding brain signals. But how do you know which ones are actually the best? How can you compare them fairly so the whole field can move forward together?
Right now, the field is a little bit like the Wild West. This table kind of shows it. One group might test their model on one set of tasks.
Another group uses a completely different dataset and different metrics. You end up trying to compare apples and oranges, and it makes it almost impossible to know what's really working best. It actually slows progress down, because it's hard for anyone to build on anyone else's work.
So, to bring some order to that chaos, researchers knew they needed a standardized test, a common yardstick, a fair way to measure all these new AI systems against each other. They needed to build a benchmark.
So the kinds of AI we're talking about here are often called foundation models. The easiest way to think of them is like these huge general-purpose engines for understanding the brain. They get trained on massive amounts of brain signal data first, and then you can fine-tune them for specific jobs, like decoding speech or maybe even recognizing emotions.
And that brings us to the solution, a project called AdaBrain-Bench. It is basically a standardized, super rigorous test for these brain foundation models. You can think of it like the Olympics for BCI algorithms. It creates a level playing field where every model competes on the exact same events with the exact same rules, so we can finally see which one really performs the best.
And the process itself is pretty straightforward. Step 1, a researcher submits their model. Step 2, the benchmark standardizes all the test data so it's consistent. Step 3, the model gets tested across 7 key BCI tasks. And finally, Step 4, it gets a comprehensive score. That way, you can directly compare it to every other model that's gone through the gauntlet.
So why does something like this matter so much? It might seem like boring, behind-the-scenes stuff, but this is what really puts the pedal to the metal on progress. By creating that level playing field, you let the best ideas win. You push everyone to build more robust AI that works for more people. And what does that all lead to? It's the fastest way to get safer, better, and more accessible BCIs to the people who are waiting for them right now.
Seriously, the trajectory here is just breathtaking. And it leaves us with this one last incredible thought to chew on. If we are truly on the verge of decoding speech from the brain, what's the next great human barrier we could overcome?